On Fleming's left-hand law. Okay, I've tried to move things around on my screen so that you can see me and the presentation at the same time, because Fleming's left-hand law is one that really gets students quite confused and is quite annoying. All right, what I hope you'll see is it's fairly simple. What Fleming's left-hand law is doing is it's allowing us to link three quantities. Okay, now those quantities are the electrical current, the magnetic field, and the force on an electrical conductor. Okay, and you can see in the image there how these things link up. We're going to use our left hand rule, our left hand to do this. We're going to use three fingers, and we're going to make sure that they're always at right angles to each other. Okay, so we're essentially looking at X, Y, and Z directions. Okay, so here we go for it. Okay, we can use this rule in order to determine the direction of a force, that's one of our fingers, on a current when it's in a magnetic field. And in order to do that, we need to be very, very clear about which finger represents which quantity. We'll start off with this finger. This is our first finger, and this first finger represents the field. Okay, specifically here, the magnetic field. Okay, we're not talking about electric fields, we're talking about electric current, which will come next, but we are thinking about the effect of the magnetic field on that electrical current. So just be really, really careful. Okay, the first finger field, FFF, first finger field. The second finger represents what we call conventional current. Okay, so we can just call current for now, all right? Current flowing from positive to negative, and that is our second finger. So that's this one, okay? And the way that you might want to remember that is second, okay, current, second. It's a bit of a arbitrary way of remembering it, however, that's just the one way we do. So we've got first finger field, second finger current, okay? The thumb, okay, the thumb represents, well, when I was learning this, we said motion, because what we have is those fields and currents combining to push the wire, and therefore it moves. So the thumb is the motion, or in a more scientific sense, the force. So we've got these three vectors all combining, okay, to produce essentially to produce one another. The field combines with the current, and then that produces a force. Okay, and you can see how these guys are oriented, okay, in the picture. They're always at right angles. If it is not possible for them to be at right angles, then it is not possible for there to be a force, and we'll talk about that a little bit later. Okay, one thing that students get a little bit confused by is the direction of the magnetic field. Okay, and you can see in this diagram, we've got some magnetic field lines there, the red ones. Okay, they are the red ones. But there's no direction on there. That's actually not a good diagram, okay? The direction of the field lines is always from north to south. So why don't we try this then? Okay, we've got, if I try and line up my fingers here, I've got my field lines pointing from north to south. I've got a current, and it's quite clearly in there. And what you can see is that the force is pushing this guy up. Okay, so the one that's shown in the picture there, slightly difficult, is at an angle. The field lines are going from north to south, the current is from positive to negative, and the force is kind of up on this guy. Now what we could ask is, what would happen if we reversed one of those guys? Well, let's take a little chance at this. I might want to reverse the current. Well, what I can do is simply reverse the direction of my second finger, current, and that just involves me rotating my hand. Okay, notice my field lines are still pointing along this way, okay? But I've changed the direction of my force, my current, and that has changed the direction of the force. When the current was pointing this way, okay, so towards the wall behind me, okay, that brings an upwards force. However, when we rotate that round, we then make a downwards force. Okay, we could also change the direction of the field. It's quite awkward, but it ends up being me pointing my hand to myself. Okay, it's really difficult for you guys to see that, obviously. Okay, but then you should be able to convince yourself that by keeping that same current, we've got a downward force. Okay, so changing the directions of these two things, current or field, will change the direction of the force. Okay, this is taken directly from a past paper. What you can see here, okay, is we've got current, which is into the page, and we've got a set of magnets. So again, what we have to ask ourselves is does this sort of diagram make sense? Well, if you look here, we've got north to south, so therefore field line, which is what's missing on the diagram, is pointing from right to left. Okay, so if I take my hand, it's quite awkward. Okay, if I take my hand, it's quite awkward. My field line is pointing from right to left as I point to the screen. Now, if I then think about the other fingers, well, the current is into the page, so that's going away from me towards the screen. Okay, so you can see my middle finger pointing towards you. That's a bit rude. Okay, and then you can see my thumb is pointing up. And so that's the direction of the force. So this diagram is correct because we've got field from right to left, current into the page, and then force up. And again, I could ask the question, well, what happens if I reverse the field? Well, reverse the field, current stays in the same direction, force changes with the field. You notice my middle finger is still pointing towards you guys. However, the force is now down because the field has changed its direction too. Okay, I could then do something similar. I could keep the field in the same direction now and reverse the current. And what you notice is my thumb goes up as well. So reversing those currents, or reversing those fields, will change the direction of the force accordingly. So anytime you're asked a question about how we might reverse the direction of a force, really think about the interaction of those currents and those fields. Okay, I hope that makes sense. Looking forward to seeing how you get on with today's questions.